Hi everyone, my name is Travis. I'm going to be talking with you about some problems in quantum state tomography. If you have some feedback about the talk, please feel free to tweet me at Travis_SCH. That would be super, super cool. I'm a graduate student at the University of New Mexico, and I also work at Sandia National Labs. So broadly speaking, my work focuses on the ideas of characterizing quantum devices. Why? Well, because one day we hope to take all of these small quantum devices and eventually put them together to build quantum information processors, kind of like CPUs, if you will. And then we hope to take all of those quantum information processors and actually build a full-scale quantum computer that might do some interesting computations that we can't do classically with this laptop, my smartphone, a supercomputer, etc. But before we can get to the stage of computation, we have to understand how to control things. And as the visitors at Jurassic Park realized, you cannot control that which you do not understand. As such, my work focuses on characterization. That is, an experimentalist builds some kind of, oh, please come in. We're just getting started. An experimentalist builds some kind of device. Maybe it produces some quantum state. And they say to me, Travis, I have no idea what state this device is making for me. Can you please help me figure out what's going on? That's the goal of my work. And there are several architectures or platforms that we've been thinking about building quantum information processors on. So for instance, Google has been investing in superconducting circuits. Sandia and NIST have been thinking about ion traps. Sandia also has a very good program in using quantum dots. We have no idea right now which of these platforms is actually the best for building quantum information processors, so we're just investigating all of them and seeing what pans out. There's one particular platform that I'm especially interested in, but that's not very well understood, namely photonics. What I mean is that we could use photons themselves as a way to transmit and store information. Why might we want to do so? Well, for one thing, light is the fastest thing in the universe, so it would be very quick to transmit information from point A to point B. Secondly, light tends not to interact with things a lot, which means that it will retain that information and not lose it to its environment. And in fact, this is actually a problem that people in classical computation have been thinking about building photonic chips that could interface with this laptop. The problem is that we don't quite understand how to characterize the useful quantum states of light that might go into such a photonic device. The reason for this is simple and complicated and frustratingly awesome. It's that light is big in terms of Hilbert space, a bit too big, if you will. Now, what does this mean? Well, when we take quantum mechanics, we learn that the way that we're going to represent quantum states is through something called the density matrix. That is, to every physical system, we map it onto some matrix, and it's got these matrix elements and whatnot. People in quantum optics will tell you that in addition to the Husimi Q function, another very useful representation comes to us from something called a Wigner function. Now, the problem is that formally speaking, this density matrix is infinity by infinity, and that Wigner function is defined over the entire plane, which means that if you want to characterize a quantum state of light, what must you do? You either need to specify an infinite number of parameters, or I should say, you need to specify an infinite number of these matrix elements, or you need to specify the value of that Wigner function at every point in the plane. And if you go to any statistician and you say, hey, I took some finite amount of data, and I'm going to try and estimate an infinite number of parameters, do you know what they will do to you? They will laugh at you, just like they laughed at me. Thankfully, though, estimation problems come up a lot in physics. We've encountered some of these in maybe our undergraduate courses. I have a falling object. I took some data. I want to make a model that describes what's going to happen. That is, we want to be able to predict the future evolution of this system. So in that sense, estimation is kind of a very natural thing that we might want to do. The main problem is that this infinity and the quantum state space in quantum mechanics just makes the problem so much more complicated. This problem is simple. It has a few parameters, and statisticians actually understand pretty well the right ways to go about doing this. This thing has a lot of parameters. It's not very well understood. You know, I could always just throw up the it's quantum and so therefore it's hard sort of argument. So the central question of my research for the past, well, a long, long time is there a finite dimensional estimate that is a good model? That is, can we take this infinite dimensional Hilbert space and can we cram it down into something smaller that also adequately models our data? Of course, what does it mean to be good? Thankfully, statisticians have thought about this problem a lot. And they invented an entire field that's called model selection. The idea being, I have a question. I have some data. I don't know how to fit this data. I'm going to generate a whole bunch of models to do so, and model selection will help me figure out which one is the best. Essentially, model selection chooses the best model. We're going to qualify what that means in a second. So for instance, if we looked at this plot, and in green we have a linear fit, and in red we have a quadratic fit, which one of those do you think looks better? Maybe it's 1, maybe it's 2. I mean, come on, the data kind of look quadratic. We want to have a statistically well-motivated way to choose between models. And that's what model selection is going to do. It does so by observing that what you mean as being the best model depends upon how you score the model. Right? Good scores are good models. There are a whole bunch of tools we can use to actually go about scoring models. Some of these tools go by the name information criteria. One information criteria that apparently everyone in the statistics community loves to use to do model selection is called the Inaccuracy Information Criterion, or AIC. So my work has been focused on asking the question, can we use the AIC to find a good finite dimensional Hilbert space into which we can cram this estimate of our quantum state of light? So we have to do some math. This is the only math formula in the entire talk, I promise. So the AIC of a model, that is the score that we're going to assign to the model based upon the data that we have taken, is computed as follows. First, oh, so sad, compute goodness of fit. Goodness of fit in green, right? We want high goodness of fit with the data. Otherwise, what is the point of having the model? But you can always fit data really, really well if you add a whole bunch of parameters to your model. Hence, we add a complexity penalty. The AIC trades off between these two. We want to increase goodness of fit with our model. The AIC penalizes overcomplicated models that manage to fit the data better. What we've come to realize is that there's a key assumption in the AIC that turns out not to be true for quantum state tomography. Namely, the AIC assumes that every useless parameter that you add to your model can contribute up to 1 unit of goodness of fit. And you can kind of see that because if goodness of fit goes up by 1 and number of parameters goes up by 1, you have a minus sign here, they both wash out. So what does it mean for a parameter to be useless? Well, essentially, useless parameters are parameters that you don't need, but that could be fit. So for instance, going back to our falling object, why can't you fit a cubic to this data? I mean, physics tells us that the time dependence of falling objects is not t cubed, but if you didn't know that before the fact, you could do so. So a useless parameter in this case would actually be the coefficient of that cubic term, because we know a priori that you only need up to t squared, but you could add t cubed if you wanted to. So it turns out that when you really sit down and think about the AIC and how it was derived, there's a very, very subtle relationship essentially between uselessness and goodness, which I realize now, having said that, is kind of a weird thing to say. Essentially, the AIC assumes that there are no constraints on your parameters. There are no boundaries in the parameter space that you're searching over. Quantum state tomography has the feature that every finite dimensional Hilbert space sits on the boundary of a larger one. Therefore, when you try and use the AIC, it breaks down. And this can be illustrated in a classical context. Essentially, constraints mean that parameters are not independent. So what I've drawn here is the classical 3-simplex. So for instance, imagine a 3-sided die, if you will. There are 3 outcomes, but because the probabilities of those outcomes have to sum to 1, you only need 2 numbers to describe that die. That's why you can represent it in R2. So if your parameters are in the center here, you can move in 2 directions, varying 2 of the probabilities, and the third one being constrained by the normalization. But what happens if your model sits on an edge? Well, then one of those probabilities actually goes to 0. And you can only slide in 1 dimension. The number of effective parameters here is 1. The number here is 2. What about the vertex? How many parameters are there then? It's a big fat 0. You are completely constrained by normalization. The AIC doesn't take that fact into account. essentially it says count all of the number of parameters. It doesn't matter whether or not you've set some to 0. As such, the AIC should not be used. What this means is that we need new model selection tools to do quantum state tomography for characterizing quantum states of light. We need some effective parameters. We need to think really hard about how many directions you can move in a particular Hilbert space as relates to it being on the boundary of another one. And unfortunately, this might depend upon the true values of those parameters. So, in sum, quantum devices, photonic devices, characterization, AIC, lots of effective parameters. Thank you.